So here we're continuing exercise 5.9, where we're looking for all the chiral centers in this molecule, and then once we find them, we have to say whether they are the right-hand version or the left-hand version of that handed center. So anytime, we saw a couple shortcuts for finding these. Anytime you have carbons in double bonds, those carbons can form maximum of bonds to three different things max. So those can never be chiral. To be chiral, you have to be bonded to four different things. So instantly we know the carbon double bonded to that oxygen is not chiral. These carbons are not chiral. CH2s are never chiral because they are bonded to two hydrogens. So that's two of the same thing. And so we have another thing where you can find the chiral centers. Usually chiral centers have solid wedges or dashed wedges, so like coming out or going away from you. And those wedges are giving you the three-dimensional orientation of the bond, and that usually only makes a difference if it's a chiral center, because it's that three-dimensionality that tells you whether it's the right or left-hand version. So probably these are chiral centers. We should always check, and we should always check for other places, but it seems like here there isn't another chiral center. You might wonder maybe about this one, because for sure everything to the left is a chiral center. I mean, everything to the left is one thing. And you also have a hydrogen coming out of there. So that's definitely a second thing. But if you look, going one way around the ring and going the other way around the ring is actually the same. You run into the same features the same distance away. So both ways of going around that ring are the same, and so that is not a chiral center there. So our only two chiral centers are the ones that we have noted here. So let's start with that one on the left, and let's try to figure out if it's R or S. So right-hand or left-hand version. So the first step is to just figure out assign priorities for the atoms bonded to the chiral center. The atoms bonded to the chiral center based on the atomic number. And I should say, just so you can see that they really are chiral. For the chiral center on the left, you have this weird group on the left. And remember, when you're identifying chiral centers, you're thinking globally. So whole groups attached to that chiral center. For the right, you have a huge chunk of the molecule, which is definitely different from what we saw on the left. We have the methyl group coming out, so that's a third thing. And remember, if you ever have a tetrahedral molecule, two of the bonds will be going in the plane, one will be coming out at you, and one will be going away. So the invisible bond that wasn't drawn must have been an implied hydrogen, and it must have been going away. So that is a fourth thing. So that atom is bonded to four different groups, and so it's chiral. So we have to say whether it's the right or left-hand version. So we'll assign priorities based on atomic number. First, I'm just going to write the atomic numbers. Hydrogen has an atomic number of 1. Carbon has an atomic number of 6. Carbon has an atomic number of 6. Carbon has an atomic number of 6. Well, the lowest atomic number definitely gets the lowest priority, so that hydrogen is going to get a priority of 4. But the other carbons tie. And if atoms ever tie, then you make a table. So I'm going to make a table for this carbon on the right, a table for the carbon on the left, and a table for the carbon at the bottom. Now, going backwards, all of these carbons go back to the chiral center, so that is not going to help us distinguish between them. What we want to do is see what the carbons are bonded to going away from the chiral center. The carbon on the right is bonded to an oxygen once, an oxygen twice, and a carbon. And I'm going to list those in order of descending atomic number. The carbon on the left is bonded to a carbon once, a carbon twice, and an implied hydrogen. So again, in order of descending atomic number. And the carbon at the bottom is bonded to 3 implied hydrogens. So I'm just going to list those there. Now when you compare these different tables, you don't look at the whole table all at once. You just look at one row, and only if that top row ties would you go down to the second row. Only if the second row ties would you go down to the third row. But here, none of these do tie. The one with the highest atomic number is the carbon that's bonded to the oxygen. And because of that, that gets the highest priority. That'll be a priority of 1. The one with the next highest atomic number is the carbon. That is an atomic number of 6. And so the carbon bonded to that carbon, excuse me, will have the next highest priority, so that'll be 2. And the lowest of these 3 is the hydrogen, so the carbon bonded to that will get a priority of 3. So we have assigned priorities. This is the first step for that Kahn-Ingold-Prelog naming scheme. We've assigned priorities to the 4 atoms bonded, or the 4 groups bonded to the chiral center based on atomic number. So now that we have those, we have to check to see if 4 is going away. That's the second step. And here, 4 is going away. So we don't have to do anything fancy. We can just go to the next step. We're going to go from 1 to 2 to 3. And because here we are going counterclockwise, this chiral center is going to be the left-handed version of itself. It's going to be S. And you can remember that because when you go from the top of an S to the bottom, you go counterclockwise. So that chiral center is an S. Now, there's one other place that looks like it might be a chiral center here, and that is the place that has the dashed wedge, that 3-dimensional arrangement, 3-dimensional information given. So let's see, let's just check to make sure that that is chiral. You've got this weird ring thing on the right. That's one thing. Whenever you're checking to see if you have chiral centers, you think globally. On the top, we've got this OH, definitely a different thing. On the left, we have this weird, group, different than any of the other things I've highlighted so far. And then the fourth thing we have is a hydrogen. Now the hydrogen isn't drawn in, it's implied. And because we have a tetrahedral carbon here, 2 of the bonds are going to be in the plane, 1 of the bonds is going to be going away, and the 4th bond has to be coming out at us. So that will be an implied hydrogen. And that hydrogen is a 4th thing. So we have 4 different groups bonded to that atom. That means it has 4 different sides, like your hand, so it is handed. It's chiral. And so it comes in 2 different versions, a left-hand version and a right-hand version. So we'll go through the CIP rules, the Kahn-Ingold-Prelog rules, to assign priorities and then figure out whether it is R or S, right or left-handed. So first, we'll assign priorities based on atomic number. The atomic number. Now, when you think about, when you do what we just did, seeing if something's chiral, you think globally. But when you're assigning priorities, you think locally. You go 1 atom at a time. So just looking at the atoms immediately bonded to this chiral center, this hydrogen has an atomic number of 1, the oxygen has an atomic number of 8, the carbon on the left has an atomic number of 6, the carbon on the right has an atomic number of 6. So the one with the highest atomic number has the highest priority, so here that will be the oxygen, because 8 is the highest number. The one with the lowest atomic number gets the lowest priority, that'll be 4, so that's the hydrogen. And the 2 carbons tie. Whenever you have atoms that tie, make a table. And we're going to be looking at the 3 things that these carbons are bonded to, going away from the chiral center. This carbon on the right is bonded to a carbon and 2 hydrogens. The carbon on the left is bonded to a carbon and 2 hydrogens. And when you compare these tables, you don't look at the whole table all at once, you just look at the top row. Only if that ties would you go down to the next one. And it does. We have 2 carbons here, so we look at the next row. Only if that ties will we go down to the next one. And that does tie, so we go to the 3rd row, and that ties too. So what that means is that we're going to go to the next atom over, further away from the chiral center. So we were, on the right side, we were here. We're going to be going here. That is a carbon. On the other side, we were here. We go to the next carbon over. That's another carbon. And because they're both carbons, we'll use a table to, we'll use a table to figure out which one has the higher priority. So let's think about the three things each of these carbons are bonded to. This carbon here is bonded to a carbon, and an invisible hydrogen. So in descending atomic number, that would be carbon-carbon, hydrogen. This carbon on the other side is bonded to an oxygen, and carbon. So in descending atomic number, that's oxygen, carbon. So now we can compare these going one row at a time, and already at the first row, we can see that the carbon on the left has a higher priority because it's bonded to an oxygen. So the branch that has that carbon bonded to the oxygen gets the second highest priority. Remember, the first one was the oxygen. Of these two, the branch on the left has the higher priority, and the one on the right has the lower priority. So we got that from these tables. Okay, well, the second step is to make sure that 4 is going away. And 4 is not going away, it's coming out at us. So we need to keep that in the back of our minds. When 4 is coming out at you, you still go to the next step, you just flip or switch the configuration that you would otherwise expect. So if you go from 1 to 2 to 3, like this, you're going counterclockwise. So you would expect that, usually, to be S, but 4 is coming out at you. So you switch it, and it's not S, it's R. And you switched that because 4 is coming out at you. So this chiral center here is a right-handed version of itself. That is the right-handed version of itself. So in order for this antibiotic to work, this chiral center on the left has to be left-handed, and this chiral center on the right has to be right-handed. If it weren't that way, if they were both left-handed or both right-handed, or if they both switched, this antibiotic would not function, and your patient would not get better. Because those handednesses are determining how the molecule fits into a receptor site. Notice again, common trend. Biologically active molecules tend to have chiral centers because our body is very chiral. So many atoms in our body are chiral. And the other thing to notice is that we have a ring here. That helps to give us a relatively rigid structure. Okay, that adds rigidity to the structure, which helps it fit into receptor sites a little better. And we can see those same two features in this next one, D. We have a couple rings. That's helping to give it some rigidity so it fits reliably into receptor sites. And it looks like we probably have some chiral centers. Now we know off the bat that any carbon that's involved in a double bond will not be chiral. Also, CH2s are never chiral because they're bonded to the same group, hydrogen, twice. That's true for these, for that too. So the places where it seems like we could have a chiral center are the places where they give us the three-dimensional arrangement of atoms in space around a carbon. So those solid wedges that tell you the atom is coming out at you, those dashed wedges that tell you the atom is going away from you. So let's look at these one at a time. See if they're chiral, and if they are, let's see whether they're right or left-handed. So for the one that's in red, that is starred in red here, we have a purple group, long chain, with what's called a carboxylic acid at the end. It's a carbon double bonded to oxygen, single bonded to an OH. So that's one group. On the right, we have this weird ring where you hit a nitrogen really soon. So it keeps going around, but I'm going to look at that. And then on the left, you have a ring, but you hit a sulfur immediately, so that's definitely different from going the other way around the ring. And the fourth thing that's here is not drawn in. Now notice only 3 bonds are drawn around that carbon, but it doesn't have a formal charge, so it must have 4. That means 1 bond is there that's not being drawn. If you ever have a tetrahedral carbon, it's going to have 2 bonds in the plane, 1 going away from you, and the 4th one will be coming out at you. And because this wasn't drawn, it must have been an implied hydrogen. That's the only atom that can be there without being drawn. And that is a fourth thing. So that starred carbon is indeed a chiral center. It is bonded to 4 different things. And so, just like your hand, it's going to be handed. It comes in a left and a right-hand version. And those left and right-hand versions are going to behave differently. They'll fit into the world differently. And so, they'll fit into the world differently, and so we need to see which hand it is. So we'll do that by following those CIP rules, the Kahn-Ingold-Prelog rules. The first step is to assign priorities based on atomic number. So when you're trying to figure out whether something is chiral, like we just did, you're thinking globally. You're looking at huge groups. But when you try to figure out the priority of those groups, you think very locally. You think just about the atom that's immediately attached to the chiral center. And only if they tie would you go further than that. So going around, the 4 things here, we have the hydrogen, which is, just a second. So we have hydrogen whose atomic number is 1. We have a carbon whose atomic number is 6, another carbon whose atomic number is 6, and a sulfur whose atomic number is 16. So if you look at the box on the periodic table, you'll see a 16 at the top of that. So we know that sulfur has the highest atomic number here, so that's going to get the highest priority, and that is a 1. Hydrogen definitely has the lowest atomic number, so that's going to get the lowest priority. That's a 4. And then the 2 carbons tie. So whenever atoms tie, you want to make a little table. I'm going to make a table for this carbon on the right and a table for the carbon sort of going down. So for the carbon on the right, now you're going to go away from the chiral center, because going back to the chiral center is the same for both of these carbons. So that's not going to help us tell them apart. So we're going away. We're looking for the 3 things that this carbon is bonded to. It's bonded to a nitrogen, a hydrogen, and a carbon. Now, in order of descending atomic number, nitrogen has the highest, it's a 7, then carbon, which is 6, carbon, which is 6, and then hydrogen, which has an atomic number of 1. So that's the order we put those in that table. For the other carbon, this carbon going away from the chiral center is bonded to a carbon and 2 implied hydrogens. So a carbon and 2 hydrogens. Now when you compare these, you don't look at the whole table all at once. You just look at the top row. Only if that ties would you go down to the second row. It doesn't tie here. The carbon on the right is bonded to a nitrogen, which has a higher atomic number than the carbon. And so the carbon on the right has a higher priority. So that's 2, and this down here would be 3. So that's the first step, assigning priorities based on atomic number. The second step is making sure that group 4 is going away. Now, group 4 here is not going away, it's coming out at us. And that means that we're still going to go from 1 to 2 to 3 and see what configuration that would give us. But because 4 is coming out at us, whatever configuration that gives us, we're going to switch it. So for example, here, if you go from 1 to 2 to 3, you go clockwise. So you would think that it would be R, the right-handed version. But because 4 is coming out at you, you switch it. It's not R, it's S. So this is actually the S, the left-handed version of itself. And again, we switched that because 4 is coming out at us. So that chiral center is the left-handed version of itself. There were 2 other places that we thought might be chiral centers. Let's think about those. They were the places that had the 3-dimensional arrangement drawn in. So the first one was the one right next door. Let's see if that's chiral. It's bonded to a hydrogen, that's definitely one thing. It's bonded to a nitrogen right next door, that's a second thing. right above, it's a carbon and then a nitrogen and a carbon on the other side. That's a third thing. And to the left, you have a carbon and then a sulfur and another carbon. That's definitely different from any of those other pieces. So you can see that that carbon is bonded to 4 different things. And so it is chiral. It's handed. It'll have a left and a right-hand version, and each of those versions will fit differently into the world. So for us to have a functioning vitamin B here, a functioning biotin, we need a certain hand. So we'll see what hand that is. The first step in figuring that out is to assign priorities based on atomic number. So the atomic number for carbon is 6, the atomic number for hydrogen is 1, for nitrogen is 7, and for carbon is 6. Well, we can see that the highest atomic number gets the highest priority, so the nitrogen is going to get a priority of 1. The lowest atomic number gets the lowest priority, so the hydrogen is going to get a priority of 4. The 2 carbons tie. Now, if atoms ever tie, you want to make a table to help tell them apart. So I'm going to have a table on the top for that carbon there, and a table sort of to the left for that carbon there. And we're going to think about the 3 things these are bonded to going away from the chiral center. So the carbon on the top is bonded to a nitrogen, a hydrogen, and a carbon. In descending atomic number, we'd have the nitrogen with an atomic number of 7, carbon with an atomic number of 6, and hydrogen with an atomic number of 1. The carbon on the left is bonded to 3 things going away from the chiral center: a sulfur, a carbon, and a hydrogen. So sulfur has the highest atomic number, 16, then carbon, 6, then hydrogen, 1. So now that we have these 2 tables, we can compare. You never compare looking at the whole table all at once. You just do one row at a time, starting at the top. Only if they tie would you go down to the second row. Here they don't tie, though. We have a nitrogen and a sulfur. Nitrogen has an atomic number of 7. Sulfur has an atomic number of 16, and so sulfur has the higher atomic number, and the carbon bonded to the sulfur will have the higher priority. So that carbon will be 2, and then the carbon on top will be 3. All right, so that's the first step, assigning priorities based on atomic number. The second step, make sure 4 is going away. It's not. The 4 is coming out at us because it has that solid wedge. So that means that whatever we do, we're going to have to switch the configuration. So we still go from 1 to 2 to 3 like normal, but after we do that, we switch the configuration because 4 is coming out at us. So here, if you go from 1 to 2 to 3, you're going clockwise. So you would think that the configuration would be R, the right-handed version. But 4 is coming out at us. And that means that we have to switch that configuration that we would have expected. So this isn't going to be R. The configuration for this chiral center is going to be S. This is the left-handed version of itself. And again, the reason we switched that was because 4 is coming out at us. So this chiral center is the left-handed version of itself. There was one other place where we had what looked like could be a chiral center because the 3-dimensional, the solid wedges and the dashed wedges were drawn in. And that was on top. So let's see if that is a chiral center. Let's see if it's bonded to 4 different things. To the left, it's bonded to a CH2 and then a sulfur. So that's interesting. On top, you've got a hydrogen, definitely different. On the right, you have a nitrogen. That's definitely different. And then on the bottom, you have a carbon bonded to a nitrogen right next door to it. Another carbon on the side. So those are indeed 4 different things. And so that carbon at the top with the red star next to it is indeed chiral. It's going to come in 2 versions, a right-handed version and a left-handed version. And we need to go through those CIP rules to figure out what we have, because only one version will have the proper biological activity. So we assign priorities based on atomic number. So the atomic numbers for the stuff around here, we have nitrogen, which has an atomic number of 7. Hydrogen with an atomic number of 1. Carbon with an atomic number of 6 on top, and then a carbon with an atomic number of 6 on the bottom. So nitrogen has the highest atomic number, so it gets the highest priority. number 1. Hydrogen has the lowest atomic number, so it gets the lowest priority, number 4. The 2 carbons tie, and anytime the atoms tie, you make a table. So we have a carbon up here at the left and a carbon below. Going away from the chiral center, the carbon at the left is bonded to a sulfur and 2 hydrogens. So in descending atomic number, we put the sulfur on top, then the 2 hydrogens. The carbon at the bottom is bonded to a nitrogen, a carbon, and a hydrogen. We put those in descending atomic number. So now we compare these tables, one row at a time, sulfur with nitrogen. Sulfur has the higher atomic number, and so the carbon bonded to the sulfur gets the higher priority. So that's 2, and then below it, this carbon down here is a priority of 3. Okay, so that's the first step, assigning priorities based on atomic number. The second step is making sure that 4 is going away, but here 4 is not going away, it's coming out at us. And what that means is that after we go from 1 to 2 to 3, whatever we get, we're going to have to switch it, because 4 is coming out at us. We only do that when 4 is coming out at us. So we go from 1 to 2 to 3. Now it looks like we're going counterclockwise here, so you would expect normally that it would be S, but 4 is coming out at us. So we switch it, and the configuration is actually R. And we only switched it because 4 is coming out at us. So that chiral center with this red star there is actually the right-handed version of itself. It is R. And so every time, and you eat this vitamin regularly, or else you would have vitamin deficiency diseases, and every time you eat this vitamin, whether in cereal or in bread, you're eating a molecule that has 3 chiral centers, and the specific chirality of those is S, S, and R. You have 2 left-handed versions and 1 right-handed version, and that fits perfectly into your enzyme pockets to help this vitamin help your metabolism, aid in your metabolism. So we have 2 more of these to do in this exercise, but I'm going to do those in another video so that these don't